All right, so now we are recording. Okay, so anything you say will be recorded, and that's fine. So we're going to do the test on Friday this week, not Wednesday. And that's not on you, that's on me. I'd wanted to have all 5 videos up by now, but I had a very busy and awesome accomplishing weekend, but I did not accomplish things for your recordings. So don't be shy about talking. Probably no one's ever going to hear this. Probably not even going to put this one online anywhere.
It has like 17 views. Hi, future Nate.
Very nice. Hi, future Nathan. Yeah, so a lot of the videos on my channel don't have a lot of views. There's also, if you looked at my channel, the entire fall semester given by another lecturer, Chris Bruin, is up there. Chris Bruin is a really, really good AP physics teacher. And he was teaching with kids with a little more background than you have. He was teaching at the Science and Engineering Magnet. And so the kids were in their third year of physics. So they had a year of physics honors. Then their second year of physics was like AP 1 and 2 combined in one class. And their third year of physics was physics calculus based, mechanics and E&M in one class. So it was their third, actually their fourth credit in physics, because they also had one credit, one whole class. It was nothing but labs the entire year. So they just show up, and so they have a lecture class and they have a lab class separately. So it's actually their fourth credit in physics in high school. And so by that point, he doesn't do as much background work, he just kind of dives in. So some of his lectures, if you want to dive into, listen to the same topic we're doing in class from a different voice, great place to go. There are some other great places to go that I'll send you as well, because sometimes we'll go over stuff in class, and what you really need to hear is you need to hear someone else explain it to you. Okay, because the same is true for me. If you hear one person talk about it, that's great. If you hear 2 or 3 other people teaching the topic from a different voice, you're like, oh, I'm really getting this from this person, that from that person, that from person C. I can really put it together. And so that's a very valuable thing for you to have, is to have people to go to that you know that are teaching the material well and that you can rely on. So we'll continue to put out some resources on the internet around that. So today, assignment 1 and 2 are due. You can either hand me paper now, or some people just snapped it on their phone and sent me a Google Doc of the photos. Okay, that can be done. If you don't want to tear out paper from a spiral or something, that's fine. If you haven't photocopied it and you want to keep your original notes, that's fine. If you want to give me your original notes and I will just give them back to you, that's fine too. I'm okay with any version of that. Yes.
For the last 2 questions, 22 and 23.
You don't have to do it. I'm not grading those.
Awesome.
Not on assignment 2? 1? No, assignment 2. Assignment 2, if you watch the video, I said I'm not grading the last 2. You can, with a TI Inspire, you can do it in no time. You put it in Solver, but you're looking for 2 angles, and it requires all kinds of sines and inverse sines and yada yada junk.
You can't do it on our calculator.
Really?
It's not the CX, it's the CAS.
For the CAS.
Yeah, so I have to download it on the free version on my laptop. My art says it only does linear equations.
Really? Not sinusoidal? Huh. Interesting. So which one do you have here? You have the CX or the CAS?
I have the CX. Right, I downloaded the free version of the CAS on my laptop to do that.
Oh, that sucks. Yeah. And another resource, if you're ever looking for calculators to solve problems, I prefer actually if you don't, because that way I can flip through it a little more easily, and I'll just get a paper clip here for you. Where would I find said paper clips here? There. Is Wolfram Alpha. If you ever want to solve any kind of really complicated math problem, Wolfram Alpha is the basis for Siri on iPhones. Wolfram Alpha is used to be one of the most complicated mathematical tools out there, called Mathematica. Okay, and they now have kind of released it, just 20 years ago. They now kind of released it on the internet for free. And so you can solve almost anything on Wolfram Alpha. You can also find out really random information about everything, about where you are right now, what's going on in your life. So when I was at the beach this summer, I would say, when is high tide? And it would search where I am. And Siri wouldn't go to the web for the information, it would go to Wolfram Alpha, because that's the basis for Siri anyway. And she'd go, according to Wolfram Alpha, and it would print the entire tidal tables along with graphs as to where I am right there on the Earth, which is really cool for the beach. And so we'll use it here in physics class as well. I can say, what is the acceleration due to gravity right where I'm standing? And it'll search Wolfram Alpha, and it'll figure out, the United States government has figured out due to all the geological surveys. They made very sensitive measurements of G all over the Earth, and they needed to know that in order to put missiles in the right place. Okay, they need to know the slight tug of gravity everywhere as it changes, and it turns out it's not straight down here. It's down, south, and a little bit east. But the south and east components to gravity are about 10,000 times weaker than the downward component. So, but there is a south and east component, and it's because of some big heavy rock, it must be in the mantle or in the crust that's a little bit to the south and east of us. Okay, mostly south. So, really interesting information in Wolfram Alpha, and a really good way to solve problems. Okay, so any questions over 3? So you had some questions. You want to talk A4? Okay, and if you feel lost on 3, you know, 3 is the hardest, I think, of all 5 of the assignments. You disagree? That's totally fine. You think 4 is. Okay, well, let's dive into 4. So I'm going to make 3 due next time, because I put up the video on Friday on how to do it, and we'll make 4 and 5 due on Friday. If you want to turn them in next time, you can turn them in next time. Okay, but they're not due till Friday. Also on Friday, you will have a test, and the test will be over these problems verbatim. Okay? Yes?
Equation formula sheet for the,
Yes, let me definitely get you that ASAP here. Let me see if I have them here. So I did say I would get you that today, and so I shall. What I shall do is email it to you. PDF, and it comes from the College Board. So the formula sheet you will have all year long is the formula sheet you will have on the AP exam. It has 1 page of reminding you how to do all the calculus derivatives and antiderivatives you will ever use on the AP test. And it has 1 page of physical constants, like the mass of an electron, the mass of the sun, the mass of Jupiter, in case you want to work a gravity problem between the sun and Jupiter or something. And then it has 2 pages of maybe only 1 page. 1 or 2 pages of just physics formulas, okay, that we're going to be using in this class. And every formula we've had so far is on that formula sheet, okay, that is that we've used in these packets. So our basic formulas of kinematics are there. F equals ma is there. The frictional formula equals coefficient of friction times normal is there. Okay, all those things are there. So let's jump into assignment 4, which I didn't open. Let me open that in a tab. And again, my off periods are A2, A4, B1. And so if you have any tutoring in your off those periods, does that work for all of you?
A2 and B1.
Okay, so if you have 2 of them, you have A4. None of them. You have A3 off?
Yeah. Yes.
Okay. I have study hall in this room. And so I will have, 15 quiet freshmen working. And so if you want to come by, you have my permission to come by. I don't want to open that can of worms to everybody. But if you want to come by A3, that works for me also. Kaya, do any of those work for you? A2. Okay. So all of you have at least a period you could come by if you need to and ask me any questions. And it is my hope to set up a Google form and put a link at the webpage for this class, the bulletin board or whatever. So you guys can just click on there and schedule tutoring, so that way I'll know you're coming, and I'll make sure to be around at that time. But if you want to informally just mention in class, hey, Brown, I need help today, A2, that's also fine. All right, so I'm going to move on to 4 and 5 today as far as talking in class and kind of finish up 4 and 5 and any questions next time. And again, the questions that you'll be on your test on Friday will be these exact same questions, pretty much word for word with different numbers. So if you know how to work these problems, you should know how to work the test. The test is meant to be an easy A for everybody. It's not meant to be a punish you grade. It's meant to be, you know what's on the summer assignment grade. Okay? Because if you know that, you don't actually know physics yet. What you know is you know how to crunch numbers and problems. But you still have been exposed to a lot of different topics of crunching numbers and problems, and it will help us to really hit the ground running, okay, when we start for real one day next week before retreats. Yay.
Retreat is already next week.
Yeah.
Really?
Yeah, it's on the 8th, 9th.
ACT is next week too.
That's easy for you guys. That's easy.
All
All right, so I'm on 4 now, and it starts off here with problem number 1, which is pretty complicated. And this is circular motion stuff, okay? So if you can imagine whirling a ball in a circle on a string, and I think the problem's also here on the board. So if you can imagine whirling a ball in a circle on a string, what holds the ball in a circle? The string does. The string does. And the string has tension. The tension happens to be centripetal in this case. So I would not call the force a centripetal force. And this is that's okay. It is a centripetal force in this case. You're not wrong. But I want to get a little picky on notation. Some people misunderstand circular motion stuff, and they just call everything that points in circles centripetal forces. And what they're looking for in the AP test is looking for you to understand that the reason that the ball is going in a circle is because of an interaction. That's a word I use a lot when I discuss forces. They're looking for you to discuss things in terms of an interaction between a ball and a string. Okay, so the ball is going to make some kind of, that's not quite a circle, I apologize, some kind of circular path like this. And they're looking for you to have the understanding that there is an interaction between the string and the ball that causes a force of tension this way. Now, is that force centripetal? Yeah, it is, because it points directly to the center of the circle. And there's no other forces pointing to the circle if there's no gravity, okay? The difficulty in this little situation is when you write down the F equals MA for the problem, and you say sum of the forces equals MA. I'm going to put an A with a subscript C. What that subscript C here means is centripetal. You may remember circular motion from freshman year. You may not. If you don't, it's okay. It's been a long time. So we'll refresh your memory. I'm not going to prove the formula geometrically right now. Okay. I'm instead going to just put in a V squared over R. Okay. That is what AC equals. And so it's weird and crazy that when you're going in a circle at a perfectly constant speed, that the magnitude of the acceleration to the center equals V squared over R, okay? And that is the formula that comes out for it. So once again, as we cover the entire semester of physics in like 3 or 4 days here, I'm not actually expecting you guys to learn physics. I'm just expecting you to learn how to crunch some problems and be exposed to these ideas quickly. Okay, and then we're going to slow down and draw this stuff out, for weeks at a time as we go through these units and make sure the conceptual bedrock is in place. So this V squared over R term over here, this is the centripetal acceleration. If you multiply times mass, you get centripetal force. In this problem here, it turns out there's more than one force acting on the problem. There's also gravity going on. And so we're going to have to look at the ball at 2 specific spots. I'm going to in this problem, even though only the top matters for this problem. I'm going to look at the top and the bottom. And what I want to do here is I want to draw some forces that are acting at the top and bottom. How many of you have been on a swing set in the last 5 years? No, not at all? Okay, how many of you can ever remember being on a swing set as a child? Okay, what did you feel like? The others have no recollection of their childhood. Yeah, they were very damaged, okay? What do you feel on a swing set? Some places you feel heavy, some places you feel light. Where in a swing set do you feel heavy? At the bottom. Yeah, right at the bottom. And at other places you feel light. Where do you feel light? When you're at the highest points of motion, either in the front or the back. You even get little butterflies in your stomach if you swing high enough, because you feel kind of weightless for a second. You get up to the top there. There's a lot of amusement park rides that also make use of this feeling, okay? So I'm going to draw some forces of tension that are toward the center of the circle at different points around the circle. And then I'm going to add in another vector. I'm going to add in a vector here for a force of gravity. Okay, so I want you to notice something really obvious about my force diagrams or free body diagrams. Those are 2 words that are synonyms that I use for the arrows that I'm putting on here. The arrows represent forces. Okay, so again, just to slow down a little bit, there's some things I said in the video for free, but we'll say them again. So I have an arrow here that's red, an arrow that's blue. Those stand for different interactions. The red arrows that I drew are for string interacting with the ball. The blue arrows are for the mass of the earth interacting with the ball. Okay, so there's different objects interacting with the ball. Each one gets its own arrow for its own force. What's obviously that you can just see from the picture, from the bottom of the motion to the top of the motion about my forces, it's not the same.
At the bottom, the force is F plus 3, T plus 3, at the bottom is T minus 3.
Okay, at the bottom, you would subtract the forces because they're in opposite directions. At the top, you would add the forces because they're in the same direction. Okay, I'm going to add one more vector here. This is not a force. Please do not draw this as a force. This is going to be drawn to show direction, it's not a very good arrow, of the acceleration. So the acceleration in each case is to the center. Because I'm in circular motion. That's why I know at the bottom, the red arrow is way bigger than the blue. Because I'm accelerating straight up. So there's a tug of war between red and blue. Red has to win by a lot. Because it's got to accelerate up in order to make the turn and stay in the circle. This is why you feel heavy, a swing set at the bottom. Why do you feel heavy? Because you're being pushed up so much. You're accelerating up so much. Okay? So I'm not just looking at number one. I'm trying to look at the whole situation of a ball on a string moving in a circle. At the bottom of the circle, to do F equals ma, you would subtract the tension and gravity. At the top, you would add them because they're both in the same direction as the acceleration. Okay, now let's go to the question. The question's going to ask us almost like a little derivative idea here. They're going to ask you, hey, what happens in the limit where there's no slack left in the rope at all? Right? And I'm going to look at the exact wording of this. It says the cord does not become slack. So we're looking for the limit where the tension of the cord is getting less until it's almost about to go slack. You know what slack means? Everyone good with that? Slack means that it's actually no longer taut. It's no longer tight. It actually begins to bend. The string actually begins to get some movement, looseness to it. You don't want that. What is the limit, the absolute limit? And you can think of the word, you can think of the calculus idea here. We're taking a limit as we get to that point. It has to be true at that point. Yeah, I'm looking at the top situation up here, okay? So I'm looking at, oh, I don't want to green because I already have a green thing. Let me do this. So I'm looking up here, and I'm asking you, how does this problem change, simplify in some way when we take the limit to where there is no tension in the string, where the string is about to become slack?
Zero.
The tension goes to zero. How could you stay in a circle if the tension goes to zero?
You're moving. It's just not on the string. I don't know what the word for that is.
I bet your coffee's like perfect temperature if you haven't started drinking.
Everything's gone.
Oh, my apologies. All coffee is consumed. Good for you. I just want to make sure we didn't forget about it and have them get ice cold on you. The tension has to be zero, but my question to you is something a little bit different. I said, how can it stay in a circle if there's no tension to hold it in the circle? The gravity is the centrifugal force. Gravity alone keeps it in motion. Now think about it. If you were actually whirling a ball in a circle, what would you have to do to approach this speed where the tension would be zero and stay in a circle? Would you go faster or slower?
If you go really fast, it's gonna like pull really hard. Like it's like spinning really fast. So you go like as slow as you possibly could. So like so it just barely stays.
It turns out you can actually physically do this. We're not going to right now in the interest of time, but you can go get a ball, a string, and you can whirl it slow and whirl it fast and see which one has more tension in the string. In order to get this to the point where the tension is zero, you'd have to slow down. Let me show it to you mathematically, okay? So let me show it to you as far as the math goes, and I'm going to write it out like this. Fg plus Ft equals mv squared over r. Okay, do you agree that if this term is 0, then V will be smaller. I'm assuming M and R are constants. M and R cannot change. V is the variable. If this term is 0, then V is smaller. If this term is like 10,000, then V would be larger.
V is smaller than 1.
Well, that would depend on the values. Smaller than 1, that would depend on the values of M and R. Okay, so let's plug in some values. Let's see how much this problem simplifies. By the way, this is I'm going to say, out of everything you have to know in circular motion, this is one of the really good things to know, one of the top 10 problems to know in your head, because it's such a quote-unquote classic problem. Gravity, of course, is m times g. It is mass times the acceleration due to gravity is the amount that the weight of gravity pulls down on you. Okay, so if I look at the math of this problem, this simplifies even further. This first little arrow that I drew through with a 0 and said, hey, tension 0, that's because I want to take the limit where the rope's going to be slack. I can also take these two masses out like this, and now I have g, the acceleration of gravity, is v squared over r. That's why they don't have to give you mass in the problem. They don't even have to give you mass, because mass cancels out. By the way, this is why all people can ride a roller coaster. It goes upside down. All people do not fall out, because mass cancels out of the problem. Big people, little people, fat people, skinny people, doesn't make a difference. Your mass doesn't matter. Everyone feels the same acceleration due to gravity, 9.8 meters per second every second. And so on roller coasters, everyone can ride it and no one falls out. Everyone feels the same butterflies in their stomach. That's a feeling from the acceleration. Okay? So let's carry on. All you need is R,
What is R?
radius of the circle. I have a circle and R is my radius. Yes.
Why is the tension 0?
Because what they asked you to do is they said in the problem, the exact words over here, Kaya, it says, so the cord does not become slack. It wants the minimum speed. It wants you to go as slow as possible to where the cord is about to go slack, and it's not going to stay in a circle. So if the cord does go slack, what will happen is, if it's going around in a circle like this, instead of continuing in the circle, it'll kind of like drop and come down there instead. Because the string will actually go slack. So rather than having a straight string like this, it'll actually be a wavy string like that.
Yeah, but I don't, then why does that make the tension 0? Because it's not, it's still attached to the ball.
It is.
Still kind of moving it, it's like not a straight.
So we're taking the limit to where the string, which was perfectly straight, is about to go bendy and have no tension at all.
So it has no tension when it's bendy.
It's
Right.
pulling it out.
When it's bendy, there's no tension. Right. And so we're taking that limit to the minimum speed where it doesn't quite go slack. So do we reach the point where tension's 0? Maybe not. We reach the limit where it's approaching 0. So since it's a math problem and we're adding the term mg plus something almost 0, we should ignore the almost 0. Okay. All right, so we're covering more than just the problem here. We're covering ideas of circular motion, ideas of forces, ideas of limits, and this is a really good example to look at. So now I have the square root of 9.8 meters per second every second times r equals my speed v. And this speed actually has a name. This is called the, I say it's a name. It's often given a phrase, critical velocity. Critical, obviously, if you're in critical condition, it means like your life's at risk. That's not what we mean here exactly. But this is a critical speed. If you go any slower, you lose your circular path. If you go any slower than this speed, you will not maintain a circle at the top because there will be no tension. The rope will go slack and it'll bend, and you'll start to move in some other shape. Okay, so this is the minimum velocity or the critical speed you need to maintain a circle. Numerically, what'd you get for an answer? Anyone? 1? Yeah.
I got 4, 7.
It should not be squared, right? Because it doesn't ask you for velocity or speed. 4.47 meters per second. Okay, is the answer suggested by Kaya. Someone else can do this. You can do it very fast here because they give you a radius, right? The radius, you don't need the mass, by the way. The radius is right here. It's 0.603. So you can just do it in a calculator and just do 9.8 times 0.603, square root the sum, 0.603.
Oh, because that's R.
Oh.
I'm getting a different answer.
Yeah, I got, he's right, or, yeah.
2.43.
I used the wrong, he's right.
Okay.
So sorry.
This at equals.
Yeah, so the velocity is 2.4. The units are meters per second because our radius is meters, right? And our acceleration just due to gravity is meters per second squared. So we end up with the square root of meter squared on top, second squared on bottom, and we get meters over seconds as our final units. I'm talking a lot of math out loud. If I need to slow it down or write it down, let me know.
So the mass here in the case is just a distraction.
No, it's not a distraction. Some people actually would have taken this equation right here, and they would have plugged in mass on both sides. Obviously, you plug in mass on both sides, it's right. So I worked the problem more symbolically with letters at first, and I didn't plug in until this very last step. And so I didn't need the mass. You could say the mass is a distraction, or you could say the mass is not totally needed. Some kids who worked this problem would not have easily figured out, Johnson, that the two masses cancel. And so they would have wanted the mass in the problem because they would have, as soon as they see the mass, they just want to do mg and find gravity. Right? They don't think it through with the letters necessarily. Okay? I've worked this problem since I was 18. And so, not every year, but on a regular basis, on and off. And so I intuitively do certain things that are not obvious to someone who sees it for the first time, right?
So the mg on the left-hand side is the weight of the object.
It's the weight of the object. Yeah.
So what is this formula like for? Like mg equals m squared over r. What is this formula for?
Okay, so this is F equals ma for this problem. Okay, so Newton's second law,
Oh,
F equals ma.
I got it.
Is the equation the one FG plus FT equals, is that like the original, like actual equation?
No.
Cancels that.
Okay, so the original equation is F equals ma. I would have started here from Newton's second law, where I'm going to take all of my external forces and sum them up. In this case, tension and gravity, there's two of them, okay? And I'm going to say that the sum of these external forces result in an acceleration toward the center of my circle. And the acceleration is v squared over r, okay? So some really important components to kind of put together in the problem. This,
V squared over R is specific to circles.
it is. So this right here, this is kind of like, I'm going to say, like step one in the problem. To figure out the acceleration is v squared over r. That's step one, okay? Step two in the problem is I'll leave it the same color. Step two in the problem is to figure out that you're supposed to have two forces. Okay, so that's like step two. Step three in the problem is to say, hey, I know that this is zero.
You add them because it's both going in the same direction.
Correct. Correct. Right, and that's exactly what we set up here at the top. That we're adding because they're both the same way, and they're both in the same direction as acceleration. We would subtract them at the bottom because they're opposite directions.
So we didn't subtract in this case. So why?
We didn't subtract because we were only concerned about the top. Only wanted to find the speed up here. What's going to happen to the ball here, Jonathan, is as it goes down to the bottom, it's going to pick up speed. It's going to pick up speed because its potential energy is decreasing as it goes down, down, down. And gravity does work on it. It makes it go faster as it goes down, down, down. So here at the bottom, it would go faster. And then it would slow down again as it went up again. Okay.
So if you want to find the speed at the bottom, we're just still ft minus f.
Yes, if we wanted to find the speed here, wrong one, Brown. If we want to find the speed here at the bottom, right here, then for this, what I would do, let me change colors, is I would do ft minus fg equals m v squared over r.
So v squared over r is for acceleration.
It's for the acceleration when we're in a circle.
So this is a fixed formula, right?
It's a fixed formula.
It's gonna be in the formula sheet.
It'll be on the formula sheet. It does not change. And it's written on the formula sheet. I will show you two different ways it's written. Let me just pause for a second and show you, this is how it's written on the formula sheet. It usually has absolute value bars here. The absolute value bars mean ignore direction. We're just talking about the speed, not the velocity, because no matter where you are in the circle, it always points toward the middle, toward the middle, toward the middle, toward the middle. And this, they're going to write equals this, omega squared over r. Omega, you remember from trig or pre-cal or something. If you do like sine of omega t, are you with me?
I don't think that is wrong.
Yeah, you did. You should learn the same letters, maybe. So this is some kind of angular velocity, and this is a time. Yes or no?
Is that like a theta, or
It's
is that
a
similar
what?
I
to?
took lowercase
Sign what?
A lowercase, you guys use an alpha?
or no.
This is an omega.
That's not omega. So
That's an omega. It's a lowercase, it's W-ish, radians per second.
Yeah.
Yes. So it's an angle change of radians per second. Was that in pre-cal or was that in calculus?
That was in Khan Academy. I don't remember.
You would not have learned it in physics. You would have learned it in either pre-cal
Oh, no. I don't
We didn't do it in
really-
or you would have learned it in calculus from Ms. Freeman. You didn't do it in calculus?
No.
How interesting.
We didn't do that much physics. What?
I'm not asking you to do physics per se, but this is whenever you graph, this is a math thing. Whenever you graph a sine function, okay, a sine function has points, yes? So I'm gonna draw really quick. Yes, you with me? That's one cycle of a sine wave. Okay, it has points. And so if you ask how long it takes to get through half a cycle or a whole cycle, are you with me at all? The time it takes to get through one whole cycle is called a period.
Yes. Yes.
Okay, and how many radians did you carve out through one cycle? 2 pi. Okay, so we have this idea, and this omega that I just defined, it's 2 pi radians per whatever the time is. I'm going to use a capital T for it, like this. Not a lowercase t for any time, but a capital T for the period, the time for one cycle.
So the T is
Okay, so the capital T is the period there. Okay, so this is how omega is defined. It's 2 pi radians per time seconds. It's radians per second. Okay, and this is how we define omega. And so this is not meant to be some weird physicsy thing. This is math. This is just saying, hey, here's how we define the idea of where the sine wave is supposed to carve out. Now you can plug in any time t you want, and it'll tell you exactly where you are in the wave, in the cycle.
Can you explain the difference between lowercase t and capital?
Yes, this is a number that doesn't change. This is a variable. So this is actually, this is the time axis right here, Nathan, and this point right here is time capital T. Maybe it's 2 seconds. So if I put a 2 seconds here on the bottom, I'd have 2 pi over 2 seconds. Omega would be pi. What does that mean? Well, that tells you how quickly that this sine thing goes through its motion. It takes 2 seconds for one cycle to go by. Now, lowercase t. Let's say that lowercase t is 1 second. Okay, so now I write down sine of pi. Please remember, for our example, omega is pi, this example. Then you would multiply 1 second. Okay, what is sine of pi? Anyone know? 0. It puts us right here on our graph. Right there. That is pi. Remember, 2 pi is a cycle, so pi is halfway there. Also, I said capital T would be 2 seconds, so 1 second would be halfway there. Lowercase t is a variable. You can plug in any time you want, and you're going to figure out where you are in the sine curve. You can actually plot points.
So capital T is the total time.
Capital T, capital for one period,
Yeah.
one cycle.
One second.
Yes, it's a constant. Okay.
But it could change.
The period of this class is 85 minutes. It does not change. So if I plug in a time like 30 minutes, it'll tell you what's happening right now in the class at 30 minutes. So capital T is the period. It doesn't change. Little t can ask at 30 minutes, 40 minutes, 75 minutes, what's going on right now. Okay. So in my graph here, where on this axis I would put sine, right? On the other axis I put t. I have these coordinates. And if you plug in a certain t, you get out a certain value for sine. Yes.
So what do you mean omega equals to pi? Like, what is that?
This is the definition. It's a mathematical definition. And it's so omega, let me write it out in words. The phrase we use in physics is angular velocity. They use a slightly different phrase in math. And let me tell you where this is going to come out in math class. Okay, I'll say that. I'm going to end with that in a moment. We're going to come back to the physics, okay, of assignment 4, because we're straying a little bit far off into the calculus lesson, more than I want to do on the second day of class. Okay, so what is angular velocity? Angular velocity is the angle divided by the time. Think about the words. Angular velocity. 2 pi is the angle. It's the angle you cut through in one cycle, in one unit circle. Sweep out one cycle around the circle, that's 2 pi radians. And the velocity is because I want to make a rate out of it. I want to put it divided by time and make it a rate. Okay, so now I see how much time it takes to cut through one cycle. So now it is a, it's an angular velocity. It's also a constant, okay? And this is where it comes into the problem in calculus class. If I give you this, sine of 4 pi t. What is the derivative of that? Don't call the answer out loud. Just in your head. Some of you will do it fast. Some of you do it slow. But find the derivative of that, please. I'll give you a hint. You need chain rule. You got it? Everyone have 4 pi sine of 4 pi t? Sorry. My apologies. Cosine?
I just wrote it.
My apologies. Now, the 4 pi is the angular velocity. The 4 pi is telling us how quickly we're carving out the cycle of the sine wave. The 4 pi is a constant. So it's 4 pi radians per second. What does that mean? That means that you're going through 2 circles or cycles per second. Do you see that? If 2 pi is one whole circle, and you're going through 4 pi per second, and it's taking you, you're going in 2 circles per second. With it?
I would know that it's 2 cycles. Can you explain that one more time?
Sure. How many radians are in one circle?
2 pi.
Are you with me?
Yes.
So if it goes through 4 pi in 1 second, then you've gone through,
1 second.
because this is a rate in radians per second. The units of this are radians per second.
So it's like,
Let me show you in units why that has to be, and then we need to move on. So why does that have to be that it's in radians per second? Because sine is a function that operates on an angle. Okay? So if these units are radians per second, like this, and then I plug in a time, any time, the time has units of seconds. So over here, I'm going to have seconds like this, and the seconds cancel out. I'm left with units of radians, which I can do a sine on radians. You can't do a sine on seconds. So the constant that's in front of the t must have units of angle, like degrees or radians, per second, so that you can actually cancel out the seconds and be left with units of something that sine can operate on. Because sine can operate on angles, sine doesn't operate on time. Yeah? Okay, so there's a lot of overlap right here between math and physics. This is pre-cal, this is not calculus. And if Miss Kenya didn't teach this last year, that's totally cool. Okay, then we're just kind of looping back and we're adding in a few things to your unit circle, your trig. Okay, it's totally fine. Because I wanted to show you that that thing in there, that omega, is a constant. T is the variable, Nathan,
Okay.
not the omega. T is the variable. You asked me in part, well, what was the difference between lowercase t and capital T? Well, the lowercase t is a variable.
X-axis kind of.
It is. It's the x-axis. That's right. It's the thing which you are differentiating with respect to. Rest away. All right. Now, it is 9 o'clock, and we have worked one problem. But, you know, we worked the heck out of that problem. So I'm going to be done with circular motion, and I'm going to move on. Maybe gravity or something. Isn't gravity in this packet, I thought? Let me look. Yeah, it is. You're right. I teach most of my circular motion principles in this course in the gravity chapter. You're right. So I'm not going to work number 2. Okay. That's F equals ma. We do v squared over r. Number 3 is...
I was going to ask for number, are they
Yeah.
asking for a friction force or the normal force?
They're asking for a frictional force.
Frictional force.
It is. What force? No. We can work the second part of it, number 4. We can work that. And so in number 3 and 4, if you read it, go ahead and read 3 and 4 again quickly if you want to read it. I agree that this whole packet is mostly circular motion. Let me just skim the rest of this. Sorry, I know I told you to read that, but I just want to skim. I thought there was some gravity toward the end. Oh, there is. There is a little bit. Not much, though. Okay. Okay, we have 20 minutes left, though, and so we're going to try and work 3 and 4, and then I want to try and get on to at least one gravity problem before we're done. Okay? Okay, have everyone read 3 and 4? We good? Right here, Mason, we're doing 3 and 4. You can read it up here if you want, or on your paper. 3 is really simple. I'm going to work in a matter of seconds. I'm not going to spend a long time on it. As all of you drive on roads, you know some roads are pretty darn flat. Other roads bank quite a bit when you go into a turn. They bank to help you stay on the road and not slip. If you ever watch NASCAR, which I don't like NASCAR, I have noticed when I flip channels and see NASCAR tracks that the ends of the NASCAR track, where they make their big turn at the end of the track, is banked. It's banked to like 10 or 15 degrees. It's banked quite a bit. It's banked so they don't slip once again. So they can go at high speed, and you're going to see that some of the normal force of them pushing into the track actually becomes centripetal force. Yes?
Have you seen that? I don't know, I saw this video of this Olympic sport. It's like bike racing.
Yeah.
But the surface they're riding on is really
Incline, like 20 degrees or something. Yes. And that is they can go very fast.
Yeah.
So that's they can go very fast without falling. Yes. Okay, so let's work this problem. First, I want to kind of sketch the problem. So I'm going to sketch 2 views. Okay, this would be a top view down, looking at the problem. Right, and over here, here's my car. Okay, like this. And this is my radius. Okay, and I'm going to make the car going this way. This is my velocity. Okay, so those vectors are not forces. Those vectors are radius and velocity. And if I do a front view of this, okay, here is my bad rendition of a car coming at you. Got a little thing here. Hey, no laughing. Okay, and so here's this thing coming at me. and its force is going this way. The centripetal force is going this way, and it's being supplied by friction. There's friction of the tire on the wheels when you turn the wheels, making the car stay in the circle. You've probably all driven cars before. You've probably all driven on slippery conditions, like say a wet road or an icy road. And if you drive in that kind of condition, you may have felt the car slip before. That's because you don't have enough friction to make the turn. Okay, so it's friction that allows your tires to make a turn when you turn the wheel. So it's a force of friction. That does not come into this problem. Okay, not directly. All right. So let's go ahead and actually work the problem. And we're just going to say some of my forces are going to equal MA. So that is some kind of force of friction acting on the tires. And that is equal to mv squared over r. But they give you m, and they give you v, and they give you r. So this is pretty relatively easy to find. Notice I did not write down centripetal force on the left. I did write centripetal acceleration on the right. I did not write centripetal force on the left. I put friction because I described the actual interaction that's causing it to move toward the center. And that is the tires are being pushed by the road toward the center. This is more of a matter of semantics. On an AP test, they don't want to see FC. They don't mind seeing AC. AC is okay. They don't want to see FC because any force that points toward the center is adding to that overall centripetal acceleration. In the last problem, if you remember, there was two forces pointing to the center, tension and gravity. Together, they were one big centripetal force. Okay? And so they don't want to see an FC. Yes?
Could you put like FC equals or like the friction? Or if you have like the tension and gravity, put like Fg plus Ft equals Fc, like the net forces.
Yes, you could. I would say on an AP test, you're risking losing points. I don't know how I want to say it. Like I would say in every class, your teacher will tell you when you walk into an AP test, look, just don't write this. I know the graders are looking for this in a certain way. Don't do it like that. Okay, this is one of those things where the graders are kind of looking to not see FC. Okay, so what they do want to see is just what components that are pointing to the center equal mv squared over r. Okay, in this case, you just find an answer. Who has the answer here? I don't feel like doing the math. It's yeah.
So we just plug in the numbers.
You just plug in the numbers. Anyone have a check on this? So we'd have 139 multiply times 35 squared and divide by 260. It's really elementary.
Wait,
You just plug in. Here's the mass, Nathan, and here is the V, and here is the R. I mean, it's plug. We sometimes call this in physics plug and chug. You don't even have to think.
So we don't even need the gravity.
No, not yet. Now, for this problem, you don't even need to know physics. You really don't. All you need to know is the equation, and you plug in the numbers. And that's why I said this week, I'm not really teaching you physics. I'm teaching you how to plug and chug these problems for now, so you have some exposure to these topics. Okay? We'll go back and slowly unpack all the concepts and ideas with labs and discussions in the next few months. Okay, great. So we have an answer. All right, now let's go on to part 2. Okay, part 2 is much, much different. Part 2 asks, what angle would you tip the track so that we can have a, so we're on number 4 now, part 2 of 2, and here's my front view. What angle can I tip the track so I don't even need friction? Is that correct?
Oh, that's what they're asking.
Let me double check the words it uses.
This is the most comfortable ride.
Okay, this means that we're not going to be using the frictional force. And let me tell you why it gives you a more comfortable ride. How many of you have ever been in a car? I'm sure this has never happened to you. It was perhaps driven by a teenager. And this teenager was driving a little bit faster than they had to. And they maybe took some turns kind of quickly. And everyone and everything in the car kind of slides a little sideways. Are you with me? Okay. Mason, that was a little bit too much of an affirmative. Yup. This morning. Okay. So if you take that exit off the toll road at a high rate of speed, then what happens is everything in the car, including you, feels a slide toward the outside of the circle because you're trying to move in a perfectly straight line, but the car that you're in is turning. Okay, so you have no choice except to like bump up against the car door, right? Now, to have a more comfortable ride, you would bank the track so you don't even need friction. This is why they have banked tracks. All right, so if we look at a front view of it, here's the track, and here's my car now. My car is at an angle like this. And the power of putting it at an angle like this is that even without frictional force, let me actually take these objects right here and just drag them down. That was a no. Brown, what did you just do, Brown? It asked me if I wanted to change the shape of one thing. Did not. Oh, did it again. Brown? Yeah, no, Brown's having trouble operating his software. Huh. I want to grab this, then I want to move it. What do I do with that? I'm about to give it up anyway because I'm curious, but not this curious.
Just drive slow.
You know, and that's actually a good point. That if you drive the correct speed, yeah, I want to move it. No, you're moving the aspect of that shape.
Ever actually tried driving 35 on cross?
I know.
Slow.
Huh. Okay, so I'm going to erase my words front view because I want to draw some vectors here. I want to drag that down, but it's not cooperating with me at all. Okay. C'est la vie. So I want to draw some vectors on this thing. And I want to draw a normal force like this. I'm going to call it F with a subscript N, for lack of a better phrase. And again, when I say normal force, to define that a little more carefully, it's also, you'll hear me use the words perpendicular surface force, and it's the floor holding up the object. If you watch the video for the third homework assignment I put up Friday, which if you haven't watched it, it's okay. But if you watch it, I spent a long time in there discussing the normal force and what we know about it and why, okay? Because in the interest of time, we have 10 minutes left in class today, I am not going to show or prove some of the things that I've proven earlier. I'm just going to say, hey, please watch that video for the proof of that. This red vector has two components. It has a component going to the right, and it has a component going up. So I can break it into a right triangle. Okay, and it turns out the component going to the right is pointing to the center of the circle, if you can imagine it. The component going to the right is my centripetal force. I just want to pause here and just let it sink in. So and so the other one is gravitational. Very, very good. So if this car is on a track and it's not moving up or down the track, it's just turning around in the circle, then when I draw the rest of the forces acting on this, remember, there's not going to be a frictional force here. So here I have my FG. This will be congruent to this because it's not moving up or down. We just got to think about that for a minute sometimes. It's got to sink in there a little bit. Because now you have to imagine, what do you really know about the triangle? Okay, and you know certain things about the triangle. You actually know quite a bit. You know in this triangle, you know that this side right here is the number we just found, 454, right? Oops, I'm in green. I meant to be in red. So this side of the triangle, am I getting the number correct from our last problem? 654. Thank you very much. I appreciate that. All right, that is this side. That's the centripetal force. That's the component of normal that points to the middle of the circle and keeps you in a circle. You're going to feel heavy in this car, but you're not going to feel sloshed off to the side. You're going to feel heavy because the normal force is more than your weight. Kind of like on a swing set at the bottom of the swing when it was pushing you up a lot. Because this normal force has two components. One of them equals your weight. The other piece or component equals your centripetal force. You get a Pythagorean theorem to figure out what the normal force was. They don't ask you what the normal force was. They ask you about the angle of the track. Okay? What I don't want to prove here at any great length is, if I'm doing color, blue. This angle right here has to be congruent to this angle right here. Okay? They're kind of like similar triangles. I don't want to prove the geometry at this moment, but you could prove it by showing that this angle up at the top of the circle is 90 minus theta. And then you can start to walk around all the other angles in this circle, or in the triangle, forgive me. So this angle right here must be theta because they're alternate interior, which means this one must be 90 minus theta because these two are complementary. Okay, I do that in another video. I don't want to walk through that at great length here. So we're going to have a tangent to the -1 of 654 newtons divided by whatever mg is. I don't even know what it is, but you guys can do mg. Okay, and when you do the inverse tangent of that, please remember tangent is opposite over adjacent. Okay, so I did inverse tangent of opposite over adjacent. That will give you an angle, and that angle it gives you will be in degrees, and that is the bank of the track. Good?
Okay, so that's giving you.
I'm working this problem because this problem is freaking complicated. I think it's hard to get the answer without some help.
The angle you found is the one at the top, but
Yes.
that happens to be.
The same was the hill. Yes. Now, how did I know that? Because I've worked the problem before. Not because I'm a genius or because it's obvious. It's not obvious. Yes.
So 654 newtons was the force of friction.
Correct.
Pushing it like into,
Yeah,
right?
pushing into. So
So at the same speed, actually, if you go back up here a little bit, 654 did not come from friction. It came from V squared R and M. So at that V squared, that's just the centripetal force you need to stay in a circle, period. I don't care if friction's supplying it, or in this case, the normal force is supplying it.
and when
That's the mass.
so it's part of gravity. Oh wait, no. Wait. Oh, never mind.
You're cool. You're cool. What do you want to ask?
No, I figured it out.
Okay, so let me be a little more explicit because we're running low on time, and I would like to work a gravity problem. We have less than 5 minutes, though. We're probably not going to get there. So the normal force is like this, and it has two components. One of them goes up like this, and it's equal and opposite to gravity going down. Let me go down a little further. So gravity does this. This is your force of gravity. These two are congruent. The other one is like this, and even though I told you not to write FC, for the moment I'm going to write that component is FC. Okay, and the way you get force normal is that you create that triangle where that is congruent to gravity. So the surface is pushing up and also to the center. And that is the normal force. In most cases in physics, normal forces are less than weight. This is one of those cases where it's more than weight. Okay.
Wait, did I get the answer?
4?
It's
4 degrees.
No. And number
the answer
4.
to number the problem. I got 25.6.
That's realistic.
Slide right off that thing.
My calculator is, I use my phone. Okay, we have confirmation, 2 independent people working it. 25.6 degrees is theta. Okay, that's a really complicated problem. That's one of the harder problems in the entire packet 4. It really is. Some of the other stuff on gravity at the end is kind of plug and chug. If you know the formula, which if you have seen the formula, it's Fg is capital G M1 M2 over R squared. And with that formula, you can find it. We have about a minute or two left. So once again, here's kind of the goal. Here's the plan. Next time on Wednesday, I'm going to amend the homework online. It has 3, 4, and 5. All due next time. I'm only going to make 3 due next time. Okay? 4 and 5 will be due on Friday. Okay? If you need help on 3, that gives you 48 hours to come in and get the help on 3. And I do want to help you and make sure you get it all. And then on Friday, the last 2 pieces are due, and we have a test over it. Question? This is the equation. It's called the universal law of gravitation, where capital G is a constant, Nathan, and M1 and M2 are masses, like say mass of the sun, mass of the earth, and R is the distance from the center of one of the masses to the center of the other. And Fg is the force of gravity. Gravitation. And this capital letter G is a constant. The constant is 6.67 times 10 to the negative 11th. I'm not going to put the units, they're complicated. So the G is a constant. M1, M2 are variables. Let's go ahead and break class 1 minute early because you need to wash your mugs if you had coffee today. Okay?
M is the mass.
M1 and M2 are masses of the 2 bodies. Say the Earth and the Moon, Earth and the Sun,
Okay.
or whatever else is out there.
And R squared is the distance between
The 2 objects, M1 and M2.
the middle of the object.
That's correct, from the middle of one to the middle of the other. And that's because in this formula, we're treating planets like little tiny points. We're not treating them like huge objects with size and gravitational tides and that kind of thing. Yes? Oh, I'm sorry. Yes. That's fine. I understand. No, class is over. I said class is dismissed. You can go. I said, yeah, I said we have 1 minute left, a minute ago. Go wash your mugs. Yes, we're out of here. Okay, so thank you very much.
Sorry, Mr. Brown, I just need to use red.
No, you're totally fine, dude. Everyone has a day where they need to do that.